Welcome to Easy BTech, your guide for BTech and beyond. In the today's topic, we will discuss regarding the Jfet parameters. How the Jfet parameters are classified, that we will see in the today's class. Next, Jfet parameters. To discuss the Jfet parameters, first one is transconductance, conductance or mutual conductance. GM. Second one is dynamic output resistance. Dynamic output resistance, that is RD. Third one is voltage amplification factor. Voltage amplification factor. Voltage amplification factor, mu. Okay, this we will discuss now. Okay, to understand this, transconductance. Transconductance. Transconductance is nothing but GM is defined as change in, that is, we will say change in output current by input voltage. Okay, this we can represent as GM is equal to change in IDS by change in VGS. Okay, from the graph you can see this is output characteristics. Output characteristics. If you see clearly, this region is known as ohmic region. Ohmic region. This region is known as pinch off or saturation region. And this BCD, this region is known as breakdown region. Breakdown region. Okay. Now you can see this point we will call as VP. In output we will draw a graph between IDS versus VDS. We plot a graph IDS versus VDS. Now when VDS less than VP, the transistor operated in ohmic region. Ohmic region. It acts as a resistor. It acts as a resistor because change in voltage, change in current. In this region you can say as VDS increases, IDS increases. Now you can say as VDS here to here, the current is increasing. Okay, you can write clearly ohmic region. The region is light when output voltage VDS less than VP. Then the transistor act as resistor. IDS is gradually increasing with increase in VDS. As VDS increases, IDS also increases. Next, pinch off region. Pinch off region. VDS greater than VP minus VGS. Okay, when VDS is greater than VP minus VGS, the transistor is lied in pinch off region. Pinch off region. Okay. When VDS greater than VP minus VGS, the transistor act as a constant current source. A constant current source. What happens you can see. It is a N channel. Okay, this is a source. This is a drain. Now what happens in this? Actually, when VGS or VGS is equal to VP, we will call it is a pinch off point. Okay, it means the depletion region, this depletion region is totally covered. This is now depletion region. This is totally now depletion region. Now when output voltage VDS greater than VP, then this depletion region point from this, okay, when VDS greater than VP, pinch off voltage moves away from the drain, away from the drain. It may come at this point now. Now these all are the depletion region. Now this all is the depletion region. Now it is the point. This is Vp from this point to this. This is the length. This is the total length of the channel. Now from this point to this point, this will got change in length. Means the total length is equal to, suppose it is x plus this here to here. From this point to this point it is x. X plus change in length. Is it clear? From this point to this point the shifts. Now as VDS increases, pinch off point moves away from the drain. Pinch off point moves away from the drain. Okay, that is called as a channel length modulation. That is known as channel length modulation. That concept is known as channel length modulation technique. Now in these parameters you can see, or from these graphs you can clearly see, this region is an ohmic region. This is a pinch off, a constant current can be occurred in this region. When VGS is increased beyond, when VGS is increased more and more, and VDS is greater than VP, then huge current. It means you can see here, due to this moving, a strong electric field can be existed, due to which it can break and a huge current can be takes place within the depletion region. Okay, students. Now we will say GM. Already we have seen what is change in VGS, change in what is the GM transconductance, change in IDS by change in VGS. Okay, this we will call as a transconductance. Now we will write GM is equal to IDS. IDS means we know this equation, drain current equation. IDS is equal to IDSS 1 minus VGS by VP whole square. It is a drain saturated current. It is an applied input voltage. It is a pinch off voltage. Or this pinch off voltage we will call as a pinch off voltage we will discuss, that is VP is equal to A square by this in the last class we discussed what is the pinch off voltage. Okay, VP plus V naught is equal to A square by epsilon 2 by E into ND. This all we have discussed in the last class. GM is equal to IDS. From this you can write IDS is equal to, if you differentiate this, if you differentiate IDS with respect to VGS, what you will write? 2 into IDSS 1 minus VGS by VP into minus 1 by VP. Because with respect to, from this formula, this 2 will comes here, 2 into IDSS 1 minus VGS, with respect to VGS minus 1 by VP. This we will write minus 2 IDSS by VP 1 minus VGS by VP GM. Therefore, GM naught is equal to minus 2 IDSS by VP, or we will write as 2 IDSS by mod VP. This is GM naught. Now you can substitute in this expression. We will write Gm is equal to Gm naught 1 minus Vgs by Vp. This is the one of the formula for transconductance. This is the one of the formula for transconductance. Okay, student, just to differentiate the drain current equation, you will get the Gm, or you may write in another formula for that. Gm is equal to that is change in IDS by change in VGS, that we will write minus 2 IDSS 1 minus VGS by Vp into minus 1 by Vp. This, from this you can remember minus 2 IDSS by Vp 1 minus VGS by Vp. Okay, students, we know that formula IDS is equal to IDSS 1 minus VGS by Vp whole square. Now from this it will come down, we will write IDS by IDSS by IDSS is equal to 1 minus VGS by Vp whole square. Okay. From this we can write IDS is equal to, if you write a square, if you make this square root on both sides, then we will write under root IDS by IDSS is equal to 1 minus VGS by Vp. It means in the place of 1 minus VGS you write this minus 2 IDSS by Vp is equal to, in the place of 1 minus VGS by Vp you write under root IDS by IDSS. Okay, this we will write minus 2 IDSS by Vp. This IDSS you may write 2 times, root of IDSS into root of IDSS into under root IDS by under root IDSS. This under root, this will get cancelled. You will get minus 2 by Vp under root IDSS into IDS. Okay, the formula for this is minus 2 by Vp under root IDS into IDSS. Or if you remove Gm is equal to 2 by mod Vp under root IDS into IDSS. This is the transconductance. Okay, it is a ratio of output current by input voltage. Transconductance ratio. It is a ratio of output current to the input voltage. That is known as transconductance. The formula for transconductance we may write like this: Gm is equal to Gm naught 1 minus Vgs by Vp, where Gm naught is equal to this Gm naught is equal to minus 2 IDSS by Vp, or Gm is equal to 2 by mod Vp under root IDS into IDSS. These are the forward. Depending upon given requirement, you have to choose this transconductance. Okay, students, second topic, we will go for the dynamic output resistance. Dynamic output resistance. Dynamic output resistance RD is equal to dynamic resistance RD is equal to change in VDS by change in IDS. Okay, it is a ratio of output current by output voltage by output current. Ratio of output voltage to the output current of a transistor. It is known as dynamic resistance. Now from this graph you may find the output resistance. This is a graph. Now any one the point. Now from the B point, suppose you can change. RD can be calculated. Change in VDS by change in IDS. That is this point. Now you can take this point. From this point to this point. Okay. And from this point to this point. What is the voltage at this point? What is the current? This we will call IDS1. It is VDS1. It is IDS2. It is VDS2. Now RD is equal to VDS2 minus VDS1 by IDS2 minus IDS1. You will get the drain resistance, output drain. Okay, R we will call this a dynamic resistance, means rate of change we will call as a dynamic, changing with respect to the time we will call as a dynamic. This is a dynamic resistance, means in this ohmic region, now there is a change. That is why it is known as a voltage variable resistor. In this region, the transistor can act as a VVR voltage, and in the pinch off region, the transistor can act as a constant current source. Constant current source in a pinch off region. Next, third one is amplification factor. Amplification factor can be represented with mu. Mu is equal to change in VDS by change in VGS. Ratio of output voltage of the transistor to the input voltage. That is, we will write mu is equal to, we may write this change in VDS by change in IDS into change in IDS by change in VGS. Now if it cancel, IDS get cancelled, you will get a value like change in VDS by change in VGS only. Okay, but this term can be written as change in VDS by change in IDS, RD. into this is change in IDS by change in VGS. This can be written as GM. That is the relationship mu is equal to, right, mu is equal to GM into RD. Mu is equal to GM into RD. Okay, these are the three parameters of the transistors. Students have clearly understand here which region. Now channel length modulation occurs when the pinch off point moves from drain away from the drain. When it moves away from the drain, now the length becomes decreases. When length becomes decreases, excess of electric field is produced within the change in length, due to which the transistor undergoes for a breakdown region. Okay, due to a huge amount of reverse saturation current. And these two parameters are important. When VGS greater than VP, the transistor operated in pinch off region. When VDS less than VP, transistor operated in ohmic region. Okay, the transistor can be operated in two regions. That is an ohmic region where it can act as a resistor. Okay, and the transistor can act as a constant current source when it is operated in pinch off region. Here the voltage is VGS less than minus VP into VGS. It is a ohmic region and it is a pinch off region. Okay students, this is about transfer characteristics and output characteristics and the parameters of Jfet transistors. Easy BTech, guide for BTech and beyond. Thank you.